So we may proceed at the cool roofs case studies that may be reply to these questions set before. This presentation will be made by Michele Zinzi, who is a researcher in ENEA, the Italian National Agency for New Technologies. His research activities include energy performance of buildings with special focus on materials and components for the building energy. Building envelope. He's involved in European and national projects, and he's an EXCO member in the International Energy Agency in Buildings and Communities program. Thank you, Michele. The floor is yours.
Thank you, Dania, and good morning, everyone. This presentation is about case studies, but before going into details, I would like to remind that solar reflecting materials are used in Europe and in particular in Mediterranean area region for a long time. As inferred from the photos popping up now, many shining examples still populate the region in Greece, Italy, Spain, and of course on the south side of the shore as well. So now the question is, are cool roof solution merging ancient concepts and advanced technology a suitable solution also for today's building? So case studies are an effective way to show the potentialities of the technology, since they demonstrate the impact in practice. Many cases were documented in the past year at every latitude and under every climatic condition. As an example, in the United States and Canada, Brazil, Europe, Middle and Far East countries, and Australia. Monitored buildings include dwellings, single and multi-family houses, offices, schools, commercial buildings, sport infrastructure. And the impact of cool materials application is documented through different indicators: energy use in cooled buildings, comfort analysis in not cooled buildings, roof thermal behavior. Impressive example of the latter is the graph in this photo on the right, where the temperature profile of the roof before, after, and before the application was monitored in a laboratory building in Greece. The photo below shows a house in Florida before and after the application of the cool roof, and an application in a multi-family house in the north of France is shown in the picture on the bottom right part of the slide. The upper part presents a case studies implemented in a very large commercial buildings in Italy, where not only the roof but also the air handling units were coated with cool materials. Now I would like focusing the attention on 3 case studies carried out during the EU Save Cool Roof project, in which 5 buildings were monitored to test the impact of cool roof. 4 countries were covered: France, Greece, Italy, and UK, and 4 buildings typologies: dwellings, laboratory, office, and schools. Some details about the methodology are anyway needed. Due to the limited monitoring period allowed by the project schedule, the case studies were implemented combining monitoring and calculation activities. The buildings were monitored in free-floating condition during the first phase, and measured parameters were local climatic condition, surface temperature of components and of the roof in particular, indoor parameters such air temperature and relative humidity, mean radiant temperature. The buildings were then modeled into Zinzi, a well-known and calibrated dynamic calculation tool. The detailed buildings model included climatic data, envelope and structure characteristics, occupation profiles. The model was then calibrated versus the monitored data. Target parameters were air and operative temperature of the building thermal zones and the roof surface temperature. Once the model was calibrated, calculations were performed using the initial roof system radiative property and those of the applied cool material. Alternative cooling technologies and strategies were also tested, as well as different building configuration. The first case was carried out in a school in Trapani, a town in the western side of Sicily. This photo shows an aerial view of the school area, and the case studies is this 1-floor block hosting offices and laboratories. This building is used also in summer because of teacher staffing. It has no thermal insulation and suffers of severe overheating. This photo here on the left shows the roof after the cool roof application. The treated surface was about 800 square meter, and the original roof system was made of concrete tiles with an estimated solar reflectance of 25% and infrared emissivity of 0.9. The cool roof application consists of a milk and vinegar-based elastomeric coating. Measured solar reflectance was 82% and measured emissivity 0.88. Two coats were applied on the roof as inferred from this photo here on the right. And the graph, in the middle, shows the fluctuation of the air temperature in black, the surface temperature of the cool roof in blue, and the surface of the roof not treated during the month of August. The cool roof gets up to 4 or 5 degrees above the air temperature during peak time, while the untreated roof reaches values up to 25 degrees hotter than the air. The monitoring started in late May and lasted until early September. The cool roof was applied in the first week of July, as inferred from the blue plot here in this photo, where the measuring of the indoor air temperature in a reference zone was interrupted. Aggregate results of the monitoring phase says that before the cool roof application, the average indoor temperature was 26.2 degrees, with an outdoor average temperature of 24.4 degrees. After the application, the average temperature inside the building was 27.1 degrees, but with an outdoor temperature of 28.2 degrees. After calibrating the model and run the calculation, the results show a reduction of the net cooling demand by 54%. And in this graph, we can see the initial performance in summer, and then the performance after the cool roof application. We tested also different strategies like roof insulation, night ventilation, external shading, and the cool roof was the most performing. Of course, lower value can be reached combining different technologies. 28% cooling energy savings were calculated for the same building if thermally insulated. This case study gave excellent results, also because of the building geometry, which was very favorable to the high surface of the roof with respect to the volume to be heated. The second building is a school located in a metropolitan area of Athens, area with a typical Mediterranean climate and affected by a significant urbanity island. The urban context can be observed from this aerial view. The school consists of 2 blocks, and the application took place on the roof of one of these blocks for a 410 square meters in total as application. This building has no thermal insulation, no cooling system installed. The existing roofing is made cement and gravel screed with an estimated reflectance of 20% and emissivity of 0.9. The cool roof product is a white elastomeric waterproofing coating with a very high solar reflectance, 89%, and high infrared emissivity. The photos below show a close-up of the 2 materials, the existing one and the cool application, while on the right we can see the works to make such application. The infrared real photos on the right were taken before and after the cool roof application, during the same time, the same hour of the day, but of course in 2 different days, characterized in any case by very similar climatic conditions. The 2 photos were not taken during the solar peak when surface temperature reached the maximum, but the temperature differences are still relevant. They are about 12 degrees. The calculation results that are summarized in this graph show a 40% cooling energy savings for the actual building. The simulation were also run considering the building thermally insulated, and the cooling savings were in this case about 35%. Another relevant result was the 20% reduction of peak load, which means downsizing the chiller with consequent cost savings. The calculations were also carried out in free floating condition, resulting in an average temperature reduction of 1 degrees in a reference classroom below the roof. This plot here on the right corner showed the reduction of the surface temperature between the cool roof and the original roof through the year. And we can see that during the summer period, such difference reached 20 degrees in many hours. This issue is relevant since a reduced thermal stress in the roof surface increases the lifetime of the roofing system. Now, after two well-performing Mediterranean demo buildings, we move to a completely different climate. This photo here on the right is that of a building located in London, in England, UK, a heating-dominated climate with significant cooling demand in non-residential buildings. Part of the building was used as a case study. The total area is about 140 square meters and consists of an open office with small rooms attached. The building has insulated walls and the roof is also has a moderate insulation. The building is heated and naturally ventilated with additional table fans. The roof has an original asphalt-based covering with an estimated solar reflectance of 10% and emissivity of 0.9, as we can see in this photo on the right. The cool roof application is a cool colored pink elastomeric coating. Radiative properties are 70%, infrared emissivity 0.88. This is a non-white coating, selected to provide some moderate solar gains during the winter and the intermediate season. The two thermal images below show the surface temperature, which is up to 15 degrees before and after the application of cool roof in similar climatic conditions. If we look at the bar here, the difference, the absolute values are of course lower than those measured in Athens and Trapani, but we are here in a very different climate. Concerning the monitoring, it shows a reduction of the office temperature of 1.7 degrees after the cool roof application. And after the monitoring, an extended calculation campaign led to relevant results. For the not cooled building configuration, the thermal comfort was improved, since the maximum operative temperature is reduced by 2.2 degrees, while the average operative temperature during the summer period by 5.3 degrees. The calculation for the active cooling configuration show a reduction of 3.5% of the global energy demand, which means heating plus cooling. And according to a parametric analysis, potential savings vary between 1 and 8.5% during the year as a function of different parameters. Albedo values is one of these parameters, but also such performance depends on the system set points and the ventilation rates, which strongly affect the impact of the cool roof and the performance of the building. Now, coming to the conclusion, we can summarize some relevant aspects. Case studies help to better understand how cool roof works in practice. Case studies were performed in the EU and demonstrated that technology is appropriate to reduce the cooling demand in cooling buildings and improve the comfort condition in not cooled buildings. Annual energy savings, global energy savings, are always achieved for insulated buildings. However, slightly negative results may be achieved for not insulated buildings because of the high heating demand. Cool roof applications are particularly efficient if they are coupled to the thermal insulation of the roof in renovation works. And a final reminder is needed. Cool roof benefits are not simply related to energy. Lower surface temperature extend the roofing system lifetime and reduce the urban environment overheating. Thanks for the attention.